Hello and welcome to another episode of Study Session for AP Chemistry. In this video, we'll be covering gases, and I actually haven't done an AP Chemistry video in a while, so it's I'm pretty excited. So the first topic is kinetic molecular theory, and there's essentially 5 parts of kinetic molecular theory. One is gases are composed of very small particles, either molecules or atoms. The second one is the gas particles are tiny in comparison to the distances between them, so we assume that the volume of the gas particles themselves is negligible. That's essentially saying like, you would have a bunch of tiny gas particles or whatnot, but like since they're so small compared to like the actual volume, so like if we say like this is like a container or whatever, since it's like obviously they'd be spread out like the whole thing, but since the volume of these is so small with respect to the entire volume, we can just say that like when dealing with ideal gases, we could say that their volume is negligible. Um, the third, I guess, postulate of kinetic molecular theory is that gas particles are in constant motion, moving in straight lines in a random fashion and colliding with each other on the inside walls of a container. The collisions with the inside walls comprise the pressure of a gas. And it also states that these collisions are elastic, so they don't lose energy whenever they collide. So like if you have like a surface here, the gas particle is bouncing and then bouncing back and then bouncing off it. This isn't the same particle, this is just like a different one. And bouncing back, and let's say you have a gas particle going like that and bouncing back. That's the force of those particles bouncing off, and then the resulting because so this kind of ties into physics. So your momentum is shifting or it's changing. So like you have to apply a force over time because F times T equals delta P. But that's physics, so you don't really need this about that. But basically, the force that these exert on the surface is what exerts the pressure, what causes just pressure against a wall of a container or whatnot. The next one is gas particles are assumed to neither attract nor repel each other. They may collide with each other, but if they do, the collisions are assumed to be elastic. No kinetic energy is lost, only transferred from one gas molecule to another. Okay, and that essentially says that like energy is conserved, essentially conservation of energy. The last one says the average kinetic energy of a gas is proportional to its Kelvin temperature. That essentially says the higher the temperature, the higher the average kinetic energy. So yeah, it's pretty simple concept. Okay, so there are a couple of formulas we'll need for this chapter. One is PV equals nRT, and essentially this is the pressure. P is the pressure, so P equals pressure. V equals volume. N equals the number of moles. R is a gas constant, and it depends on what type of units you're dealing with. So I typically use, whenever you're dealing in terms of atmosphere, I believe it's 0.0821. If I remember that correctly, I haven't used that in like over a year. So I'm actually pretty stoked. 0.0821, dude. See, this is what AP Chemistry does to you. It just ingrains certain information into your head. But okay, regardless, the T is temperature. And then this is measured in kelvins. Okay, and then also if you're converting from Kelvin or Celsius to Kelvins, Kelvin equals your degrees Celsius plus 273. Okay, and then the next formula you have to know. This one isn't as heavily stressed in the AP curriculum. It's that the rate of effusion of one over the rate of effusion of the second one is equal to the square root of the molar mass of one over the molar mass of two. That essentially says the rate of the first over the rate of the second. So like how fast it would get through this tiny hole or whatnot. Like the gas particles leak into like, let's say like there's a container here and then this is all open space. How fast the gas particles leak from this container is equal to the square root of the molar mass of the first gas over the molar mass of the second gas. So that's pretty much it. Okay, so let's get into some practice problems. So our first problem says a sample of argon gas, so it's A. Whoa, that was bad. Let me go back. AR. Okay, a sample of argon gas is sealed in a container. The volume of the container is doubled, so 2V. if the pressure remains constant, so pressure is constant, what happens to the absolute temperature? Okay, so we know that let's think about our constants. Okay, so we know that PV equals nRT, and we know that this is going to remain constant. This is going to remain constant. This is a fundamental constant, so it remains constant. But we know that our volume is changing, so this side times 2 because your volume is being multiplied by 2. So what's the only factor? It wants to know what change is going to occur to the temperature. So in order for this to hold true, for it to be equal, the temperature also has to be multiplied by 2. Okay, if that makes sense, because if you have 2 times the volume, so 2PV equals nRT times 2, because PV equals nRT. You essentially just multiply both sides by 2. Is what I'm trying to get at, because your other variables are held constant, so in order for that equation to be satisfied, the temperature would have to be doubled. Okay, the next question says, a sealed rigid container is filled with 3 ideal gases, A, B, and C. The partial pressure, so partial pressure is the pressure that each gas exerts on its own on the container. So like if you had a container A, B, C, the partial pressure of A is just the pressure that A alone exerts on the container. Of each gas is known. The temperature and volume, so we've got partial pressure. I don't remember how you're supposed to write that, but I'm just going to write it like this. I'm pretty sure it's something like that or whatever, but I don't really remember how to write it. You know what, I'll just use that. The partial pressure is known. The temperature and volume of the systems are known. What additional information is necessary to determine the masses of the gas in the container? Okay, so if we have P, so we can use the partial pressure, and the temperature will be the same for all of them, and they all occupy the same volume. So like P partial pressure 1 times V equals nRT, N1, and then we've got P2 times V equals N2RT, and then P3 times V equals N3RT. Okay, and it wants to know what would you need to solve for the mass of the system. So if you think about it, we have this value, so we don't need that. We've got this value, we don't need that. We've got this, we've got this, we've got this, we've got this. We have our fundamental constant, we know that. And then we've got the temperature, because it said the temperature was observed. So in each case, the only thing we need is the number of moles. And, in each case, we can actually solve for the number of moles because we know that these will be equal or whatnot. Because these are all known quantities, so we could solve for N1. So we can solve for the number of moles. In solving for the number of moles, okay, we have the number of moles, but how would we want to convert that into grams? Well, we would need the molar masses. So we need the molar to solve for the molar mass to solve for each individual mass of the system. Because we've got all these other values, we can just simply do PXV over RT, so P whatever number equals NX, and then solve for N that way. So it's actually, all we need is the molar mass of each, if A, B, and C, and we would be able to solve for the mass of A, B, and C if we have those other values measured for us. Okay, the next problem says 2 balloons are at the same temperature. Okay, so temperature equals same. Okay, and one contains 14 grams of nitrogen, so 14 grams of N2. And remember, nitrogen is diatomic, so it would be N2. And the other contains 20 grams of argon. Okay, which of the following is true? Okay, so the temperature is the same, so we know the average kinetic energy. And we also know that the molar mass is of nitrogen, so Mn is less than that of MAR, just because if we quickly pull up a periodic table. Also, if you guys ever have any questions, feel free to sign up for my website, studysession.org, and I will answer them as soon as I can. So Yeah, just because like I know I can't answer everything in this video. And so if we look at this, we've got nitrogen. We got a molar mass of about 14, but we have to multiply that by 2 because it's N2, so that's 28, and this is 39. And in fact, did I just write N2? Okay, so we know that the molar mass is less. And if we think about the formula for kinetic energy, so kinetic energy equals 1/2 mv squared, right? So the kinetic energies are the same, however, the mass of nitrogen is less. So if the mass of nitrogen is less, the molar mass, and we know based off, its average kinetic energy, so how much you have of it is not a concern. So we know that the molar mass is less, so our velocity for our nitrogen has to be greater because the average kinetic energy, it's not the total kinetic energy, it's the average kinetic energy. That's why it doesn't depend on mass. If it was just the total kinetic energy, then we would have to factor in for mass. But since the mass is lower, the velocity will have to be higher. So we can say that the average speed of nitrogen is greater than the average speed of argon. Because using our formula for kinetic energy. So that's pretty. Anytime you have two gases at the same temperature, and once you compare the average speeds or velocities, I guess speed's probably a better term at this, or in this scenario, because the velocity is kind of random. It's always going to be higher for the one with less mass because they have the same amount of kinetic energy.